My name is Nathan Wong, and this is my video on sorting algorithms. There's two main types of sorting algorithms that I'll be going over today. The first type, incremental sorting, is designed to find a sequence of solutions given a certain input. They usually work by taking a single element from the input and sorting it into various positions, eventually resulting in a sorted list. Type 2 is divide and conquer. Divide, just like my parents. The divide and conquer method solves a problem using recursion, splitting it into at least two different subproblems over and over again until the main problem is finally solved. Every method I'll talk about today falls into one of these categories: bubble, insertion, selection, merge, and quicksort, with a little bit of detail about binary trees. Now, these algorithms can be applied in many ways, from sorting cups, rearranging cards, sorting how much money you've saved over your lifetime, or even sorting how cute your limited edition Jung Kook from popular South Korean boy band BTS cards are. But I'm going to be using a little more practical application today. Say you have exactly 10 Cheetos for a snack, and your friends are all asking for some. Now, as you can see, all Cheetos are not created equal, but fortunately, neither are people. You need to figure out which Cheeto to give to your friend which you like a lot, the friend that you don't actually like that much, and the friend who's just okay. For a visual representation on how these algorithms work, we're going to go to the drawing board. Now we'll talk about bubble sort and the algorithm. Bubble sort works by steadily going through a list and swapping two adjacent elements if they aren't in the correct numerical order. For example, 1 and 8 are in the correct order, but 8 and 7 aren't, so they would get switched. 8 and 4 aren't in the correct order, so they would get switched. 8 and 3 are not in the correct order, so they would get switched. And so on throughout the list until we finally have our sorted list. This method is long and inefficient and takes a long time, and is only useful if you have a kind of sorted list already. We're going to demonstrate this with our Cheetos. I'll be doing my best throughout these trials to keep everything consistent, even though I have frail old man hands. Alright, now on to the next method. Insertion, which is Junchao's favorite kind of sort, works by taking an element and then moving it left toward its proper index. For example, 2 is in the right position for now, 5 is in the right position for now because we can't move it any more right, but 4 is not in the right position. So we can move 4 to the left, nudging everything over one index. Now going through this list, all these numbers are in the right position because they can't move right, but 3 is not. So 3 nudges every other number forward. This is more efficient than bubble because we're only dealing with one index at a time, but over a long list of numbers, it'll still be extremely inefficient. Now, let's demonstrate this using our Cheetos. Wow, wasn't that cool? Now onto another cool method, selection sort. Selective, sounds like my ex-wife. Guess what time it is? It's drawing board time. Selection sort is extremely similar to insertion sort how it works, and there are actually two different types. You can deal with the minimum and you can deal with the maximum. For this example, we'll be using minimum as it's closer to insertion sort. We find the lowest unsorted index inside the entire list and sort it back to its original position by swapping the elements. So the list would look something like this. Now, 3 is our next least unsorted index, and we would switch it with 7. We would go on and on until our index is finally sorted, but this suffers much the same problems as insertion and bubble sort. The maximum would just be dealing with the maximum and sending it to the back of the list instead of the minimum. Time to selection sort myself back into the Cheetos. That does it for the incremental sorting methods. These methods are great for really small sets of data, but as they get larger and larger, it'll take a longer and longer time to complete. And that's where a divide and conquer method comes in. Our first divide and conquer algorithm is going to be merge sort. Merge sort works by continually splitting the problem into groups of 2 different subproblems until we finally have small enough problems to deal with and sort back into our original list. So you have groups here of 6, 5, 7, 1, and 2, 4, and 9. We would then try and sort these elements independently of each other to try and make a smaller group possible. Now we can finally try and sort back into our main list. It may not look that pretty up here on the drawing board, but when you put it into a computer with tens and thousands of numbers, it can make for a pretty mesmerizing visual. Now onto the final method, quicksort. But before I can explain quicksort, I have to tell you about a binary search tree. Binary trees function on things called nodes. For example, if we take 4 as our node, it'll have 2 children, less than and greater than. If we want to insert 5 into our node, we would have to put it in the greater than. It becomes the child of 4. But if we wanted to insert 6, well, all the 4's available children are filled up for it. So 5 would become a node and host 6 as its child. It would become a huge tree as we go throughout this list, and this has many modern world applications for indexing. But this is way too complicated for something that I can put in this video, and it's already too long, I think. I don't know, I haven't edited it yet. But how does this go into quicksort? So quicksort works by taking the last element of the list and creating a pivot. Now, we'll sort it by the numbers that are greater and the numbers that are less than. We would keep doing this throughout all of our smaller groups. 6 becomes the pivot, 9, 5, 2 becomes the pivot, and 1 and 3. Now, this might look familiar, and it should, because this is a binary search tree. Quicksort basically sorts everything by making a binary search tree and loading it back into a list. This is why binary search trees are so efficient and good for indexing. But let's see that in action now with our Cheetos. It might not seem very fast here, but that's because we only have 9 elements in our list. On a list 10,000 numbers long, it can take only a fraction of a second, as if the numbers were teleporting into their place. Now that's fast, but not as fast as me. Teleporting into this random house. Now, let's compare the different algorithms.
Alright, so I used to have footage here comparing all of the different sorting algorithms of the Cheetos, but that unfortunately kept breaking my Premiere and it wouldn't render properly, so you're just gonna have to trust me when I say that insertion worked. The reason why the insertion algorithm came out on top is because there's only 9 elements and it's an incremental type of sorting algorithm. The divide and conquers don't work as fast, so the 3 different incremental we have will be the fastest, except for bubble. Bubble doesn't count. Insertion and selection are extremely similar, and it was basically up to a matter of how the lists were sorted in the first place.
Now that we know which algorithm is the fastest and our Cheetos are sorted, we can start to give them out. Jim, my least favorite, gets the smallest Cheeto. June gets this big Cheeto. And Zach gets this medium size. But this is for me. Thanks for watching.
Why are you in my house? Why do I have the smallest Cheeto?
'Cause I'm in the stars tonight. So watch me bring the fire, set the night light.